Welcome back to Calculus. In this video I want to talk more about the extreme value theorem and specifically how we can use it to actually find a max and min for a function. Right? So last video I just talked about this is how maxes and mins work, this is when you can have them and not, but we didn't actually find any. Okay, so let's remember what the extreme value theorem says. It says if you have a continuous function on a closed bounded interval, we're going to call it AB or just I, then the function has to have a global max or min. If you do not have a continuous function, or your interval isn't closed, or your interval isn't bounded, or any combination of those, if anything goes wrong, then you might not have a max or min, or you might. You might have one, you might not. You just aren't guaranteed anything. Okay? But in this wonderful case, when you know that your function is continuous, your interval is nice, it's closed and bounded, then you have to have a global max and min, and that leads to a really nice process for finding them. So let's see how this works. So to find the global max and min, in this case, so again, this algorithm only works when you have when you're guaranteed to already have a global max and min. You just do a few steps. So you make a list, and we're going to add some things to the list. First thing is we're going to put in all the critical points. For f of x that are in I. Okay, so of course you could have a global max at a local max, right? So that's the sort of thing we're looking at. We have to check all the critical points, and we have to check the endpoints. So let's say append the endpoints to your list. That's a silly way to say it. Include the endpoints in your list too. Include the endpoints of the interval. So endpoints of I in the list. So if you're a computer programmer, you've got like whatever point dot, take your list dot append this point and dot append the other endpoint. Now your list is bigger. So now you've got a list. It's got all the critical points and it's got all the endpoints. Those are the only places that the global max and min can occur, right? If you don't have a critical point, then the function's not going to be a local min or max there by Fermat's theorem. And that means that somewhere nearby that point, the function is bigger, and somewhere nearby the function is smaller. So that point isn't a max or min. It's not a global max or min for sure. So you have to have a global max or min at a critical point or the endpoints, because we saw that can happen as well. Okay, so this thing in your list, that's all the possible locations for your global max and min. And since you know you have to have a global max and min, whatever is the biggest value must be the max, just among the points in your list. And whatever is the largest value among the points in your list for the whatever is the smallest value for all the points in your list, that must be the global minimum. So all we do is we evaluate f of x at all the points in the list. And then we're done. So the largest output is the max. Let's say the largest, we'll say the largest output is the max. Or more specifically, we can call it the global max. And the largest that's not a minus sign or a time sign, but the largest or the smallest output is the min. Okay, so not so bad. One thing you should note is that you do not have to classify these critical points or the endpoints as local maxes or mins. There is no need to classify the local stuff because it just doesn't matter, right? Your max might occur at a global max or min, at a local max or min, or it might occur at an endpoint, and it doesn't matter. So there's no need to classify as local maxes and mins. That was kind of just a separate thing. So please don't waste your time doing it. It doesn't matter. Okay, anyway, let's try it. Let's see how this process works in action. So I want to find the global max and min for this function, we'll start out with something that's not too super complicated. Let's say f of x equals x to the fourth minus 8x squared. Now remember, we want to find this on some closed bounded interval. So let's say this is on the interval I equals square brackets, so we are including the endpoints, -3 to 1, square bracket on the right as well. Okay? And often I'll say, and the points where they occur. So remember, the maximum is the y value, it's the output of the function. Where they occur is the inputs to the function, so those will be the x values. The points where they occur. Okay, cool, right? Fun, yes. Well, what do? We've got a process. Yeah, I just zoomed past it. Make a list of all the critical points, then put the endpoints in too. So I guess I have to find the critical points. This is a polynomial, so the derivative is going to be pretty simple, and there's not going to be any place where the function's not differentiable, so we just have to worry about where the derivative is equal to 0. So step 1, just like with local maxes and mins, we need to figure out where f prime equals 0. So we're going to find f prime of x. That's going to be 4x cubed minus 16x. We're going to set that equal to 0. So I guess the first thing I would do is factor out a 4x. Then I've got x squared minus 4 equals 0. And then I'll factor that further. So I've got a 4x outside. I could divide by the 4, but I don't really care. It doesn't really matter if you do or not. Then x squared minus 4 factors in x minus 2, x plus 2. So please don't think you can just divide by x, because you'll lose that x on the outside that's showing that x equals 0 is a critical point. Okay, so I have critical points at x equals, well, the solutions to this equation. So x could be 0, x equals -2, and x equals +2. And that's not actually the best order to write them. That's kind of the order I thought of them first, but usually we'd write them from decreasing to increasing, so I'd put the -2 first. Okay. But anyway, now we want to do step 2. I guess I'll label that. Step 2, make a list of all the possible locations for max and mins. So the possible max and min locations, there's only 5 points to check. So I'm going to write these in order. The first one was -3. Why -3? That was the endpoint of the interval, right? Remember, our interval went from -3 to 1. So we need to include those 2 points in our list. So we've got -3, and then we have the critical points at x equals -2 and x equals 0. Then we have the right endpoint at x equals 1, and that's it. And I can see some of you saying, what about x equals 2? That was a critical point. Well, guess what? This is not an I. So we don't actually care what happens there. Our interval stops at x equals 1. That was given to us. So we don't care what happens for any of the critical points outside that. So actually, we only have 4 points to check. Huh. Okay, so that's it. That's the points we have to check. Now we just check them. So step 3, plug into f of x. So remember, this was, I'll remember, x to the fourth minus 8x squared. And we just plug each of the values in. Okay, so we'll do f of -3. That is -3 to the fourth minus 8 times -3 squared. So let's see, 3 to the fourth, the minus sign gets destroyed by the fourth power. So 3 to the fourth is 81 minus 72 is 8 times 9. So 81 minus 72, and I think that is 9. Okay? F of, let me give myself a little more room. F of -2 is going to be -2 to the fourth minus 8 times -2 squared. That is going to be, let's see, 2 to the fourth, 2, 4, 8, 16. So 16 minus 8 times 4, 16 minus 32 is -16. Okay, f of 0, that one's pretty easy. That's 0. I'll put it over here as well so we can have them all lined up. And then f of +2, well, since everything's to an even power in my function, that's going to be the same as f of -2. So that's going to be -16 again. Wait a second. I don't need to plug in f of 2. I just ranted about that a minute ago. Excuse me. F of 1. I need to know f of 1. So that's going to be 1 to the 4th minus 8 times 1 squared. That is 1 minus 8 is negative 7. Okay, so I've got these four numbers, and the biggest one is the max, and the smallest one is the min. That's it. The max and min have to occur at one of these 4 points, so whichever point is actually the biggest, that must be the maximum, right? And whichever one is the smallest, that must be the minimum. And we can see where they occurred. There could have been multiple points, right? Like if my interval it was big enough that it included x equals 2, I might have had the minimum occur at multiple points. But in this case, I really don't. So we'll say the global max is 9, and it occurs at x equals negative 3. Notice that's the end point of the interval. And the global min is negative 16. So we could say the global minimum value, or we could just say the global minimum. And that occurs at x equals negative 2. Okay, so I thought it would be useful to look at a picture of this. So this is my old friend Desmos. Actually, this is more of a new friend. So let me turn that off. So here's our function. This is x to the 4th minus 8x squared, only graphed from negative 3 to 1. So that's what I did here. If you just put something in curly braces afterwards, it restricts the domain. And you can see the 4 points we found are this negative 3 comma 9 at the very left. That's the maximum. It's not a critical point, right? Because the function would keep going after that, but we cut off the interval kind of artificially so that our derivative being 0 doesn't detect that point. But then the minimum at negative 216, that's a local minimum, so and that's going to be the global minimum as well. So your global max and min can occur at the local max or min, or they could occur at the endpoints. And then the 0, 0, and the 1 minus 7, those aren't really anything. The 0, 0 is a local max, but it's not the global max because the function goes up over on the left. Okay. Now, if we had allowed the function to continue on and like have kind of its more full domain, then it would look like this. And then we would find that other local minimum at x equals 2. And that would also be another place where the global minimum occurred. And the function would go on to the left after for x is smaller than negative 3. So then negative 3 comma 9 wouldn't be a max. But given that the domain is restricted, we're really just looking at this bit. And then we found the max and min. Okay, so yeah, pretty fun stuff. We will use this to great advantage when we do optimization and like word problems pretty soon, and I will see you then.